this on? You can hear me? Okay, so I'm just gonna start by reminding you of some things that you're supposed to know already. So if you did your homework, you know what a first order sentence is. So it's something that looks like this whole thing. And and the bound variables are the ones that are bound by quantifiers, and the free variables are the ones that aren't. And so if you have a particular ring in mind, then given such a first order formula, well, you can't quite associate to it a truth value because you don't know yet what x is. But you can think of it as a function of x, where if you substitute a value of x in the ring, then this is either true or false when you let the variables run over the ring. Okay. And it's a first order sentence if there are no free variables. So then it does have a truth value. And positive existential formula is the same thing as a first order formula, except that you don't allow the for all. You don't allow the universal quantifier, and you also don't allow not. Okay. So all right. So as I was saying, so given a first order formula. So let R be a ring. So all my rings are going to be commutative with 1. Okay. So then you can attach meaning to the first order sentences, and given a first order formula, so in general it might have more than one free variable. So that's a first order formula in the language of rings. It gives rise to a subset of the n tuples with values in R, namely the set of n tuples for which the value of the sentence you get, well, when you substitute the values for x, such that this is true. Okay, and the sets that are so I mean this has come up already in the other lectures, but just to make it clear. So the sets that arise in this way, they're called the definable sets. So this is more general. Okay, so you can do the same thing if you start with a positive, in a special case where your formula is positive existential, then the definable set you get from it will be called a positive existential set. Okay. And maybe I'll make one more definition here. So you can also, I'll say that a formula is Diophantine if it's just like a positive existential formula, except there's only one equation involved. So in other words, you don't have the and the or. So it's going to have the following shape. There exists x1, a bunch of existential quantifiers, and then inside you'll have some polynomial equation. So some polynomial in the x's, and possibly some other variables, some other free variables that are not. So polynomial equals polynomial. Now it doesn't. Usually when you talk about polynomials, you allow minus signs also in the expression. And it's not going to make much of a difference as far as the sets they define, whether I allow a new symbol for minus or not, because you can define minus in terms of plus. Okay. Yeah, so x minus y is z if and only if x is equal to y plus z. All right, so of course, a Diophantine formula. Those will be called, the things they give rise to will be called the Diophantine sets. And maybe I should say, since I already defined last time what it meant for a subset of z to the n to be Diophantine, that it's pretty easy to see that this gives the same notion as last time. Also, what's true is that for many rings R, the set of the positive existential sets are the same thing as the Diophantine sets. In other words, if you're given, so a positive existential set might have some system of equations or might have some disjunction of equations, but you can always combine them. Well, at least for many rings R, you can combine them into a single formula. So I'll maybe just sketch this briefly for the case, the proof sketch of this fact in the case where R equals Z. So, I mean, what do you do? So, well, so we're starting with a positive existential set. We want to get to something Diophantine. So first of all, the first step you can do is, given any equation, you can reduce it to an equation of the form f minus g equals 0. And now, given any disjunction of equations, you can combine those into a single equation because that's equivalent to the equation f times g equals 0. And then, given a conjunction, that will be, because we're working over z, that will be equivalent to this single equation. So if you repeat these, eventually you'll collapse any so any quantifier-free formula will be collapsed into a single equation. And as I said, it doesn't matter whether you allow minus signs or not. Okay, so I mean, this doesn't work for this doesn't work for the complex numbers, just because this last step does not. I mean, f squared plus g squared equals 0 doesn't imply that f equals g equals 0 for every ring. But for most rings, for example, you can show that for any field that's not algebraically closed, you can find a substitute for that f squared plus g squared equals 0 using norm forms, for instance. The reason for these lines at the bottom is that somebody told me that you couldn't really read the bottom line from the back of the room. So I hope it's. Okay, so this is all basic stuff. But let me continue. So just to also remind you what the first order theory is for a ring. So that this has also come up in other lectures. So the first order theory of the ring R that's just the set of first order sentences that are true for R. First order sentences in the language of rings that are true for R. Okay, and of course you can also talk about the positive existential theory, where you just take the positive existential sentences that are true, and so on. Okay, and you can say that the theory is decidable. So there's another definition. So the theory is decidable. That means that there exists an algorithm so that takes as input a first order sentence. So you have to figure out some way to encode. So first order sentence, you have to figure out some way of encoding a first order sentence as a non-negative integer. But that's, since we're always going to be talking about, at least I'm always going to be talking about finite languages, this is not going to be a problem. And then the output is supposed to be yes or no, depending on whether. Well, yes if the sentence is true. In other words, if the sentence belongs to the theory, and no otherwise. Okay, so in this terminology, you could say, for example, that Hilbert's 10th problem over Z has a negative answer if and only if the positive existential theory of Z is undecidable. Okay, but now I want to generalize this to other rings. So over various rings. So there are various ways of stating the problem. There's one subtlety that comes up, and that has to do with the coefficients of the polynomials you allow. So what I mean when I say the Hilbert's tenth problem over the ring R, so it asks whether there is an algorithm so that takes as input a polynomial. And OK, so let me for now say that f is going to be a polynomial with integer coefficients. And then the output is yes if there exists an a in R to the n such that f of a equals 0. Now this makes sense because there's always a unique ring homomorphism from Z into R, so you can make sense of this, of f of a. OK, no otherwise. Now this might not seem completely natural. I mean, you might say, why not you have as input all polynomials with coefficients in R? So the problem with that is that, well, you need to have some way to encode these for input into a Turing machine. And if your R is something like R, like a real number R, then you can't, there's no, I mean, you can't encode the real numbers into a Turing machine just because there are uncountably many of them. And so there are two options. Either you can restrict your problem, as I've done here, to the case where you have polynomials with integer coefficients, or you can, or you can enlarge the set of coefficients a little bit and say, OK, I'm going to allow any polynomial with, say, real algebraic coefficients. And that's something that's countable, so you could use those as possible inputs. So maybe I can make a second definition, a variant of this question. I could talk about Hilbert's tenth problem over the ring R. So I mean, there's a definition I'm just making up for this talk. So don't take this too seriously. But Hilbert's tenth problem with coefficients in some subset S. And that'll mean the same problem. So everything's the same except f is, instead of having integer coefficients, is assumed, the input is assumed to have coefficients in S. In order for this problem to make sense, you have to assume there's some encoding for the elements of S.
So why do you do just one input? Why don't you do a finite input?
Oh, you mean a system of polynomials, you mean? Well, you could, OK, yeah, you could. I guess I was just trying to make it close to the original Hilbert's tenth problem, which had just one polynomial input. But because of this fact, it's not going to make, for most rings, it's not going to make a difference. So if I allow a system of polynomials and ask whether the system has a simultaneous solution for most rings R that we'll be interested in, yeah, the answer will be the same. All right, so far all I've done today are give a bunch of definitions. So now let me state some results. So some of them have already come up. So I'm going to list a bunch of rings R and then ask whether the, OK, so you ask several questions about the ring. So you can either ask about Hilbert's tenth problem over the ring, or you can ask whether the whole first-order theory is decidable, which is a lot stronger. That means you want an algorithm that decides not only existence of solutions, but also to decide truth of any first-order sentence. All right, so here's the ring R. So let me start with some easy rings. So complex numbers, so this is already complex numbers and real numbers. By Tarski's result, that not only is there, so there's the elimination of quantifiers implies that you have positive yes answers here. OK, even easier, take a finite field. You want to decide whether first order sentence is true. You just decide it by looping through all the variables. That's easy to do. And OK, and as we've just heard, for p-adic fields, by which, so by periodic fields, I mean, I'll mean finite extensions of QP. So for those, again, the answers are yes. So these are all the, so these, well, excluding FQ, these are sort of the completions. And then the other local field that's of interest are the power series ring. And there, as we've discussed, there are some problems. We don't know either. Okay, so these are all, okay, well, with the exception of FQ, these are together, these form the local fields. So these are the fields that arise as completions of global fields. I guess I haven't told you what a global field is yet, but alternatively, you can view those are the same as the non-discrete, locally compact Hausdorff topological fields. If you give those the topology coming from their absolute values. Okay, so so next I can consider a more complicated class of fields, the global fields. So okay, pretend that this board is sitting on top of this board. Okay. So then, right. So I could have a number fields. So number field is a finite extension of Q. And analogous, okay, so then I can have global function fields. And those are the finite extensions of the Laurent series fields. Okay, so these are all global fields. And here the answers are, well, for Q, so Q is maybe the most interesting of the questions. So there's the no answer for the first order theory. That's Julia Robinson's work. I'm not going to say a whole lot about the history, but just to give the answers at this point. And the same, she also did the case of number fields later on. And again, well, there's no number field for which the answer is known here. On the other hand, for global function fields, it's completely answered. The answers are no. And okay, so those followed earlier work where the answers are no here. And so you can also look at, oh, I should say one thing. So for all of these, I mean, for this, I mean, I don't want to just consider polynomials with coefficients in FQ. I also want to, I want to decide equations with polynomials with coefficients in the whole ring, if you want. Or equivalently, if I add to the theory a symbol for the element t, then that's going to be, for example, then the first order theory for that will be undecidable. So, okay, so whenever I have a function field like this, so include a symbol for t.
Will the result matter? You get a different result?
Yeah, I think so.
Can you repeat the question, please?
Oh, sorry. Yeah, the question was, if you don't do this, if you don't include a symbol for t, will you get a different result? So I believe these. I think so because. Well, let's see. Okay. Well, I know that for at least for polynomial ring, the answer to ask for at least for the Hilbert's tenth problem over a polynomial ring, over FQ, it'll just boil down to the Hilbert's tenth problem over FQ itself. Because if you have a solution to a system of polynomials over a system over FQ, and you have a polynomial solution, you can always evaluate the polynomial somewhere and get a solution in FQ. And conversely, if you have a solution where if you have a solution to a system where where the entries are in FQ, then you can just view those coordinates as being polynomials, and they'll give you a polynomial.
But still, you can ask the more interesting question of non-constant solutions.
Okay, but I mean, okay, so for FQ, I guess you can, yeah, but you need some way to, yeah.
It's probably still decidable.
I'm not so sure about that. So, oh, sorry, yeah. So the question was, suppose you ask for non-constant solutions to a system of polynomials. So I haven't really thought about whether that would be decidable or not. So I'm not sure, but that's.
Existence of non-constant maps from P1.
Yeah. So then he says it's a question of non-constant maps from P1.
P is decidable, so not the
Okay. Well. Okay. Maybe I can talk to you about it afterwards. Yeah. So. Yeah. So the same thing I should do here. So. Okay. So you can also look at other function fields, like instead of having global function fields, so where the constant field is finite, you could look at function fields over the complex numbers or the reals. So here, what's known is for C joint T, they're open questions. On the other hand, for two variable rational function fields, the answers are no. And also for reals, for one variable function fields over the reals, the answers are no. So a lot of these results use elliptic curves. Actually, so does. Okay. Well, anyway, so I'm not going to say much about these results, though. So far, those have all. Okay. Again, there I should have symbols for the variables. Otherwise, it's not so interesting. So, all right. Okay, so include symbols for T and U, and U if there's a U in the field.
Is there an example with yes in the second column and no in the third?
So the question was whether there's any example with a yes for Hilbert's 10th problem and a no for first order theory. Actually, I'm not sure. Okay. I mean, you can ask. Is there any? Maybe you can construct some. I don't know of any natural example. Actually, I don't know of any unnatural example either. Maybe somebody, is there any expert in the audience who happens to know a field or even a ring for which there's a different answer to these two questions? Of course, I mean, if you have a yes answer here, then if you can decide the truth of all first order sense, then you'll have a yes for this, because this is a sub-problem of that one. So, yes?
Example is yes in the first column, but it doesn't go no in the second column. So for instance, the ring of algebraic integers in totally real numbers.
The ring of all the algebraic integers that are totally real. So that's so
Is positive, but
it's yes, but it's unknown.
maybe it's also yes in the second.
Okay, but that's better than nothing. Well, I mean, there's some other candidates here, like here, that there could be different answers. But I guess those are the other way around.
Just maybe one more question. Those no columns in the global function fields case, do you know is it because of some specific class of varieties or something? You know?
Okay, yeah, I mean, you can. It uses some isotrivial varieties, and there's.
Of what sort? I mean, like, suppose I restrict to general type. You know.
Okay, the question is what kind of varieties are used in the proof of this no answer? For varieties of general type, I mean, I'm not sure. I guess I can't say exactly what I don't remember. I mean, the proof is complicated. It builds up a lot of things, but along the way, it uses some curves of general type.
Whose proof is that?
So well, it's in the notes. I mean, this is the original proof for FQ. The original idea came from Feidas for FQ of T, where Q is odd, and then it was generalized by various people to handle the algebraic extensions and the characteristic 2 case. So Videla, Schlappentock, and Eisentrager.
Didn't the Neff do something?
I don't know about. I mean, he did something for he's responsible for the R of t. Maybe that's, and I mean, there's some other things he's done. Denef is sort of all over the place in this, but okay. The question was whether what Denef did. Okay, so so far I've only listed fields, and I've sort of tried to list them roughly in increasing order of complexity. So I mean, I don't really have a definition of complexity for fields, but you can imagine, for example, one way you could do it is you could look at its absolute Galois group and look at how big it is. So for complex numbers, it's pretty small. For the reals, it's a little bit bigger, and for finite fields, it's bigger. And QP, well, there it's still pro-solvable, but and then the Galois group of number fields and global fields are pretty complicated, as are the Galois groups for those other function fields. And you can view the sub-rings of these fields as being even more complicated than their fraction fields, just because if you're thinking about how rich the arithmetic over these rings are, you can think of them as having extra structure coming from the divisibility relation. And so that makes these rings even more likely to have undecidable theories. So in particular, for number theory, I want to look at, maybe I should use a different. Okay, so you can look at the, we already know the answers for no, for Z. So this is Hilbert's 10th problem, and this is the undecidability of first order theory. On the other hand, you can also look at the rings of integers in number fields. So this is what the students in my project will be talking about. So here K is a finite extension of Q, and this is the ring of integers, which is defined as the set of elements in K that satisfy a monic integer polynomial over Z. So that's a subring. It's in many ways it's analogous to Z, and here the answer is known to be no. In fact, you can deduce this from Julia-Robinson's result for its fraction field, for the number fields. On the other hand, here the answer in general is not known. It's known in some cases. And in the case where it's known, it's no. The answer is no. So for some OKs. Yeah, so as far as from a number theory's perspective, I guess the number theorist's perspective, the main open problems are for the ring of Hilbert's 10th problem for the ring of integers, and also Hilbert's 10th problem over Q. And so those are the ones I'm going to be focusing on from now on. So in fact, I'm going to be talking mostly about, well, the rest of this lecture and next time, I'm going to be talking about Hilbert's 10th problem over Q. Okay, so, all right, so Hilbert's 10th problem over Q. So I want to relate this to questions about varieties over Q. And so let me just say what I'm going to use as the definition of variety. Well, I'm not going to give the complete definition, but I'm going to use the definition that's in Silverman's book on elliptic curves. So I'm not going to bother with the language of schemes. For now, so a variety is going to be assumed to be, for example, quasi-projective. So it's a Zariski open subset of some Zariski closed subset of projective space. And also assume it's absolutely irreducible. So it's irreducible over the algebraic closure. Okay, so then I can now state the following result relating Hilbert's 10th problem over Q to algorithms for finding rational points on varieties. So here's a proposition. So Hilbert's 10th problem over Q has a positive answer. In other words, there exists an algorithm for deciding whether a polynomial or a system of polynomials has a solution. That's equivalent to saying there exists an algorithm to decide whether a given variety over Q has a rational point. So a rational point just, I mean, if you think of the varieties being defined by a system of equations, that just means a solution to the equation. So the only difference, I mean, between this and this is that here, well, I guess there are a few differences. I mean, here I have these extra conditions on the variety, for example, that it has to be irreducible, whereas here it could have been any single equation. And okay, I can give you some other parts to this proposition. It's also equivalent if you want an algorithm not just for varieties but for algebraic sets. So for me, an algebraic set will be the same thing as a variety, except I don't put the condition of being irreducible. So that's a little more general algorithm. On the other hand, you can make it more special, and instead of asking for an algorithm for all varieties, you can just ask for an algorithm for non-singular affine varieties. So non-singular affine varieties over, okay. So over Q again. I mean, you could go on and list a couple of other equivalent things. Like you could use abstract varieties in the sense of Weil, or they're also discussed in Hartshorne's book, where you have things that are just glued together but not necessarily embeddable in projective space. But okay, let me just stop with this list.
Okay, just one question. Can you replace it by projective variety?
Actually, that's one of the things I was going to say. Actually, I don't know the answer to. The question was, can you put another line here where you, instead of having non-singular affine varieties, you have non-singular projective varieties? And that I don't know if that's equivalent. A priori, it might be that that's actually an easier, that restricted case of this problem might actually be easier. Conceivable, I don't think it's very likely, but it could be that there's an algorithm to decide the existence of rational points on non-singular projective varieties, but not on varieties in general.
Well, for geometers, projective varieties are easier in some sense. We could hope for some big.
Yeah, so he says that geometers consider non-singular projective varieties to be easier than other varieties. I guess that's true. But I mean, they're not that much easier than the general varieties. So.
But about deciding like a number of points, for example, I mean, deciding more than just having a point, I guess projective variety and affine would be the same thing. If you required.
If you're asking a different.
More of the algorithm. Yeah?
If you ask more of an algorithm, if you want to decide, if you ask more things like to get some description of the rational points or something, I mean, I'm not sure exactly how to phrase it, but if you change the question a little bit to make the question harder for non-singular projective varieties, then maybe you could make them all equivalent. Yeah. The question was whether you could, if you change the problem a little bit by asking for more than just an algorithm for existence of rational points, could you get a more general equivalence? Okay, I think I'm going to sketch the proof of this proposition just because it involves a bunch of reductions that are also useful in other situations. So it's okay. So I mean, all of these problems, the algorithms for these problems are all special cases of the most general one. So the most general one is this one, the algebraic set. So This is most general. And the last one is most special. And then the other ones are in between. Well, okay, I guess this is maybe a little bit, I mean, there's a little special too in that it only has one equation, but okay, anyway, so for the proof of this, to show they're all equivalent, I can assume that there's suppose we have an algorithm for the most special of the problems. So suppose we have an algorithm for deciding the existence of rational points on non-singular affine varieties. Non-singular, okay, so then we need to construct. So we need to build an algorithm for arbitrary algebraic sets by using this as a subroutine. So the proof is going to be so let X be an algebraic set, and and we want to figure out whether there's a rational point on it. So algebraic set over Q, and so we need to somehow reduce the question of rational points on X to the question of rational points on non-singular affine varieties. So the algorithm is going to go by induction on the dimension. Will be by induction. On the dimension of this algebraic set. So it's going to be a series of reductions. So the first step is you can reduce to the case where X is irreducible. So over Q. So this is easy because otherwise you just write X as decomposed into irreducible components. Into its irreducible components over Q. And if you could solve the problem for the irreducible components, then, there's going to exist a rational point on X if and only if one of its irreducible components has a rational point. And also, to make this algorithmic, you also have to do this decomposition in an algorithmic way. So given the variety, given the algebraic set, you have to be able to decompose into irreducible components. But it's been known how to do that for a long time. I think it comes from a thesis of Greta Herrmann in the 1920s or something, some student of Emmy Noether. So from now on we're going to assume that X is irreducible over Q, but that doesn't mean it's irreducible over Q bar. For example, maybe I should give an example. If you have this, here's an example of an algebraic set over Q that's irreducible over Q, just because this is an irreducible polynomial if you view it as a polynomial with Q coefficients. But it factors if you look at it over Q bar. Geometrically, you get these two components, where this is y equals square root of 2x, and so on. The other ones. So I need to now reduce to the case, because my definition of variety has Q bar irreducibility in it. I now want to reduce to the case where my algebraic set is actually Q bar irreducible. So this is step 2. So I want to say that without loss of generality, I can assume that X is irreducible over Q bar. So in other words, X is a variety. So how do I do this? So if it's not, so otherwise, what do I have? If I can decompose it into Q bar irreducible components. So the Q bar irreducible components let me call them Y1 through YR. So the Galois group of Q bar over Q acts on these, and it acts transitively. Because if it didn't act transitively, then if you looked at one of the orbits, that would be a Q, an irreducible component over Q. But there's only one of those by step 1. So these are going to be permeative transitively by the absolute Galois group of Q. So the Galois group of Q bar of the algebraic closure over Q. And now where can rational points lie? So if you have a rational point on X, so this is the notation for the set of rational points. Well, what does the Galois group do to P? It fixes P. So P is fixed by the Galois group of Q bar over Q, because the coordinates lie in Q. So that means that, well, if it lies on, P also has to lie on one of these components. If it lies on Y1, then by hitting it with the Galois group, you see it has to lie on all of them. So P has to lie in the intersection of all the Y's. But then you can use, I'm really tempted to go below this line, but I'm going to try not to. So, you can just, okay, so now what is this intersection? That's going to be something of lower dimension. As in this picture. Here, in this example, what this says is that the only rational points on this curve can lie in the intersection, because anything over here would have a Galois conjugate over somewhere else. So, okay, so this is of lower dimension. So you can apply the inductive hypothesis to that. And so then by induction you can reduce to this case. Okay, so that's the end of step 2. So now we've reduced to the case of varieties. All right, so maybe I'll save the statement. So I need to reduce further to get down to a case of a non-singular affine variety. All right, let me first reduce to the case where it's non-singular. So step 3. So without loss of general A, I can assume that X is a non-singular variety. So okay, so what? So otherwise, otherwise you can write X. At least if you're thinking of X as a set, you can think of it as you can take the singular locus, the set of singular points on X, which will be a subvariety, a closed subvariety of X, and well, decompose it into it and its complement. So the non-singular part. Now, there's a theorem that over Q, or more generally over any perfect field, there's the singular locus for such a variety will always be smaller than X. You can't have the whole thing won't be singular, in other words. So but because X is irreducible, that also implies that this will have smaller dimension. This will have lower dimension. So you can use the inductive hypothesis to decide whether this piece has rational points. So in other words, if you want to decide the existence of rational points on X, you can reduce to the question of deciding rational points on the non-singular part. So okay, so finally, so now we're almost done. We have a non-singular variety now, but we want to reduce to the case where it's an affine variety. So you just use the fact that any non-singular variety is going to be a finite union of affines. So I mean, it's sitting in projective space, and you can is a finite union of affine varieties. And if you have a subvariety of something that's non-singular, then the subvarieties will also, well, okay, they're open subvarieties. So then the open subvarieties will also be non-singular. So this is not a disjoint union. This is just an open covering of the variety. So which will be non-singular. Okay, and we assumed at the beginning that we had an algorithm for non-singular affine varieties. So now you can decide it for this and going through all the reductions. So that's it. Yeah, and I guess I should have said this at each step, but all these steps are algorithmic. In other words, if you had equations for x, you could write a program that would do all these reductions. And so the reductions is all algorithmic. So that finishes the proof of this proposition. All right. So this is why number theorists and algebraic geometers are interested in this question, because in Hilbert's 10th problem over Q, because they always want to know what's happening with rational points on varieties. Okay. Yeah. So and as I said, I don't know whether you can do. I couldn't figure out any way to do a similar reduction for non-singular projective varieties. Maybe there is something, but I don't think it's as obvious as these reductions. So let's see. What time did I start? Do I have
Just before 10 past.
just before 10 past? Okay, so I should maybe take five more minutes or so. All right, so let me. Okay, so what can we? So let me make a definition of Diophantine sets, where now I'm not just talking about Diophantine subsets of Q to the n, but Diophantine subsets of arbitrary algebraic sets. So I guess I don't need this dot. Okay, so X is an algebraic set. So again, I'm not sure if I said this. The algebraic set is the same as variety, except it's not assumed to be irreducible. So it's something just defined by a system of polynomial equations.
Is it affine? Is it affine?
No, it doesn't have to be affine. No. So I want to include all varieties. So in projective, no, yeah, it's in projective space.
Algebra is
So-
in projective space?
Yes.
So something closed in projective space?
Well, I don't even want to assume it's closed, maybe. So maybe I should just say. The question was, what is an algebraic set? I mean, is it assumed to be affine or closed or what? So I want to take the most general thing. Maybe this is different. Maybe this is different from what you're used to. In fact, actually, now that I think about it, it's probably different from what's in Silverman. But I want it to be something that's So yes, quasi-projective. If you know what quasi-projective means, then that's what I want. Except I don't want it to be a variety. So I don't want it to be irreducible.
So possibly reducible quasi-projective variety.
Yeah. So possibly possibly reducible, right? Possibly reducible quasi-projective. Okay. Well, anyway, I think everybody by now has an idea of what this means. So I don't think I need to write anything. Just think about a variety. If it doesn't really matter that much, because of all these reductions, everything's going to be equivalent anyway. I just want to be as general as possible. So now suppose I have a subset of the rational points. I want to know what it means for this to be Diophantine. So I'm going to use the following definition: S is Diophantine over Q. So if and only if there exists a morphism of algebraic sets, in other words, something described by polynomial equations from one algebraic set, another algebraic set y to x. So maybe I should have said there exists a y as well, and a morphism like this, such that S is exactly the projection of the rational points from Y. In other words, S is equal to F, the image of the rational points on Y. Yeah, so this everything's over Q. I guess I should have said that. So this is okay. So this is of okay. This is a morphism of algebraic sets over Q. Yeah. Okay. Usually, I'd only want to talk about rational points on things that are defined over Q, and yeah. Okay, so here, okay, let me just make this remark. Maybe I'll end with this. So I mean, how does this relate to the earlier definition of Diophantine I had before? So I had the definition of Diophantine formula for in the language of rings, and then if you have a subset of Q to the n, it makes sense to say what it means for a subset of Q to the n to be Diophantine. So I want to say that this is the same thing in the special case where I take X to be affine space. So if I suppose X is affine space over Q, and so then S and S is a subset of affine space, of the rational points in affine space, which is just Q to the n. So then I have two different notions of Diophantine, one from this definition and the other one, which is the original definition, something that comes from a Diophantine formula. So the claim is that these are the same. So S is Diophantine over Q if and only if S is Diophantine over Q. So, okay, so I probably should write something, so in the old sense. So why is this? I mean, these are both equivalent to saying that S is positive existential. So, I mean, we already knew that Diophantine in the old sense implied positive existential because that was a special kind of, Diophantine formulas are a special kind of positive existential formulas. On the other hand, if you have something that's positive existential, you can write it as a projection of some set from some higher affine space. Because saying the set of, well, okay. To say that there exists variables, the parameters, such that a certain polynomial equation is satisfied, that's the same as saying that, maybe I should write this down, so it's, otherwise, maybe not going to be so clear. So, okay, let me number these. So 1, 2, and 3. So 2 implies 3 is easy. That's by definition. So 3 implies 1. So that if I have something that's positive existential, that means that S is given as the set of A's in Q to the n, such that there exists an X in some other Q to the m, such that some polynomial Px Ax is equal to 0. That's the definition of Diophantine, or positive existential. Well, sorry, that's not the definition. I mean, I really should have. It's probably better to do. Okay, sorry. Let's assume that we already did 2 implies 3, because that's just the merging of formulas of if you have a positive existential formula, you can change conjunctions and disjunctions and merge them into a single equation. So let me instead do 2 implies 1 here. So now S is given to be Diophantine in the old sense, which means this, that there is some polynomial P for which S has this kind of representation. Now, this P defines an algebraic subset Y in affine space of dimension n plus m. And then S, and then now you have a projection map from an plus m down to a affine space, n-dimensional affine space, which you just forget the other coordinates. So let me call that F. And then it should be, then this definition of S is the same as saying that S is equal to the projection of the rational points on Y. Okay? And okay, and then finally I need to do 1 implies 2. Actually, no, I want to do 1 implies 3 is better. So this, I'll end with this. So actually, this is probably easier to say in words than it is to write it down. So maybe I'll do that. So what does 1 implies? Oh, okay, so 1 implies. I'll just write down 1 implies 3. So what does this mean? So I'm given something, some set S that's a projection like this. Now all you have to do is take this and write it in terms of first order logic. So what does this mean? It means that there exists some point on Y such that if you map it under these polynomial maps F, you end up down there. So I mean, it's going to be some positive existential thing. I don't think I can say anything that'll make it very clear, but if you just think, you just have to think. I think this is just something you have to think about for 5 minutes, or maybe 1 minute. Okay, so all right, so 1 implies 3 is okay.
So what was Y? Was Y an algebraic set as well?
Yeah, sorry. Yeah, so the question was, what is Y here? So yeah, the answer is that Y is an algebraic set defined over Q. So this is a okay. So yeah, so this condition about being Diophantine, it means there exists. I probably should have written it this way. There exists an algebraic set Y over Q, and there exists a morphism from Y to X over Q, meaning that it's given by polynomial equations with coefficients in Q, such that this holds. Okay, so that's the end of my second lecture. So next time I'll talk about attempts to reduce Hilbert's 10th problem over Q to the question of Hilbert's 10th problem over Z, and why they haven't succeeded yet. So yeah, thank you.
Are there any other questions?
What's Diophantine over Z? What do you mean by Diophantine? Oh, you haven't put that on the board.
Well, I guess I mean you could Diophantine over Z. I mean, if you wanted to state it in this you mean this, an analogous definition. Well, this is really okay. So at the very beginning yesterday I talked about Diophantine, a subset of Z to the n being Diophantine, and then today I defined Diophantine over an arbitrary ring, and that's what I'm referring to in the old sense over here. And now this is a third definition. Yeah, and so, but they're all compatible, these definitions. In fact, you could write something similar to this over Z if you wanted to. You could imagine an algebraic set over Z and look at the projection of these integer points on Y under some morphism. And that would be equivalent to the definition of Diophantine I gave yesterday.
So is it exactly the same then, this version?
Yeah, they're all equivalent. They all give the same notion. Yeah, the question, okay, well, maybe it's clear what the question is.
Any other questions? Then, if not, thank you again. And there's a break of how long will the break be?
We start at 11:30.
We'll start, at least I will start at 11:30.
I guess a more geometric way of seeing this. last implication.